Same thing. Let me go for bagging. Bagging is bootstrapped aggregation, combines predictions from several models together. Sometimes it's more powerful and more accurate. Let's see if its power will show here. Okay. Okay. Now, look at this infected. Don't forget, correct it. So, let's run it all over again. Now it's working. It can take time. Now, look at, let me see the, oh, it has a high balance accuracy. It even has fairly high accuracy. The balance accuracy is okay. If you don't want to do data imbalancing techniques, if you don't want to go through you can just, instead of picking accuracy for imbalanced data, just pick balanced accuracy. So 55%, pick balance accuracy over accuracy, especially when it is imbalanced data. Now let's go for boosting, which is also an ensemble model. So I'm using other boost here. There are a lot of other types of boosting methods. We have the cat boost, light GBM, and all that. They are very, very powerful models. Now, in all of these, we're going to see which one is the best. We're going to see which one is the best. Okay. Now, let's run it. Boosting is taking some time to run because apparently it is a combination of prediction of models. So the next thing to do now is to either tabulate or plot all these models on the same scale, on the same line, to see how they behave together, right? Okay. So we are getting to the end lecture. So in the subsequent lectures, we are going to start considering how to handle data preprocessing alongside and the imbalanced method, imbalanced data. Now, look at what is going on here. We're now going to collect all of them together. Remember, our SVM, we use SVM model to name it as the object. If you look up there, you see SVM model. Look at it, SVM model. So just gather all the names of the models used. RF model, we have LR model, we have KNN model. We're going to put in that resample. We have NN model for neural net. We have NB model for naive Bayes. We have LDA model for linear discriminant analysis. Then we have LVQ model for linear vector quantization. And then we have we have BAG model for linear, for bagging, and then we have BO model for boosting. Right. So we're going to collect all of them here into this list. SVA model, bag model, RAM, not in any order anyway. MB model, RF model, KNM model, the same way they were spelled up there. BO model. Are we missing anyone? Are we missing out anyone? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everything is here. So we're going to have them here, and then we're going to run it. Then we'll summarize these results. It will give us the summary to rank them according to their performance, to rank all the accuracies and the kappas according to their performance. Then we are going to do a kind of box and whiskers plot of all these models. And then to the box and whiskers plot will give us a very good comparative analysis of all the models perfectly. And you'll see. Now, let me quickly talk about kappa as we wrap up in 5 minutes. Kappa has a very great advantage because it accounts for the agreement of occurring by chance. In essence, it's particularly good for imbalanced data set like we have here, where there is a high tendency that the model will favor the majority class. So kappa essentially provides a standardized metric for comparing the performance of different models. And then it is useful when we are dealing with multiple models or data. So please record your kappa as well so that we can judge. So that's another thing you can report in your research. Don't just report accuracy, sensitivity, prediction. Report your kappa. It will help us to know, because kappa ranges from -1 to 1, and the higher, the better. Now, after doing this thing is telling me subscripts out of point again after taking so much time. Severe, but it's going to be faster now. Now it ran. Okay, I'm seeing something here. Look at specificity of 90%, and sensitivity is lower. That means this model is not good enough. It's the positive that we want it to predict. It's not predicting it so much. That's the essence of this sensitivity being low, right? It's not predicting the severe so highly. It's not favoring it. But look at the kappa. Kappa has increased a bit, and the accuracy is still almost the same. Now, let me run this. Let me do all the resamples. Oh, great. And then you can see here the support vector machine carries the day. It's proven as the best model here. It has ranked it for us, followed by our neural network, and then the worst model here is likely to be the bagging. So this is a diagram you can also report. Now look at the various kappas too. Now this is how to report your machine learning models. There are more things you can do, but for the sake of time, I'm going to stop here. We try to do more later on. For instance, this is the AUC, ROC, area under the ROC curve of random forest. You can try it for all your models. This is another plot that should go into your paper. The higher, the better here. The higher the area under the curve here, the better the model. So we can compare all these areas under the curve of the ROC curve for each of the models and also put it in the paper to be able to judge the best model. In fact, this is another thing that can really take care of imbalanced data in case you do not believe the results, but you will believe the AUC, ROC curve better. Look at this one, is even lower. Can you see? So you can try this for all the other models. And then we can also compare that, or you can even report this as well on your metrics table by judging your models. Now, after doing that, we're going to now go to handling imbalanced data, but we're going to stop here. We're going to start this in our next webinar series, and it promises to be great. So I'm stopping here for now. Thank you so much for your time. I hand over to the moderator for questions. And
thank you so much, Prof, for a nice presentation. It was very well delivered, and I know my majority of participants have enjoyed your lecture. Kindly, this is a session for questions. Engage Professor with the areas that maybe would like clarification. This is an opportunity for you to ask questions. Feel free. Hello?
Yeah. Good day, sir.
Yes,
hello.
John?
Yeah. Thank you for this wonderful presentation. I am really fascinated about the lectures and everything you have discussed with us today. But sir, I am very new into machine learning. I'm a mathematician, particularly studying an infectious disease. And I have a serious desire to venture into applying machine learning into my research. I want to ask, please, all these values that is displaying when you run some things, and we have the data, when we have kappa, sensitivity, specificity, and other things. Can you just, in just a minute or 2 minutes, just try to explain to us how we can interpret that into those who are not into mathematics, who are not into statistics, how we can infer things for them from that, those range of values. So, did you get my question?
Yes, I got your question.
Thank you, sir.
I got your question. I will have to send you a material.
I will be very grateful. I will be very, very grateful.
That you can read for that. I've created a GitHub page for this group. If you join our group, Professor Dennis will send a link here to join our machine learning group.
Thank you.
We'll be sending materials from time to time so that you can understand better. Yes, now, sir. If I were to take it on one by one, we have about 10 metrics that will judge our machine learning models. If I were to take it one by one, it would take another 1 hour or so. But in essence, simply put, we have, see the machine learning models or algorithms as competing elements or models that are being used to predict data. Now, just like in an election, there are candidates that are competing for the votes of the people, whether they will say this one will do better, this one will not do better. Now, there are judges, electoral body, committees of electoral body. Some of the committee members may say, yes, let's announce this kind of. Some of them may say no. Some of them may not agree with some results. Now, that is how these metrics are: accuracy, sensitivity, specificity, kappa, log loss, and all the other metric, balanced accuracy, and all that. Now, for a particular model, the accuracy is being computed, and the accuracy measures the proportion of correctly classified instances out of all the instances. Maybe you are predicting a disease. The ones, you see, when people, like the malaria case we just considered, when they go to the hospital, do you know that some people have been misdiagnosed before? Isn't it? They thought it was malaria, but they are treating, they thought it was another disease. They are treating another disease, isn't it? The doctors do make mistakes. So also the machine learning algorithms, they can make mistakes. They can predict some things in error. So that is why we calculate accuracy to know, are you predicting all the positive cases well? Some of them, they are only based on predicting the negative cases, like the sensitivity. Some of them, like the precision. Precision indicates the proportion of true positives. That is, those who really have the disease, and the algorithm is saying they have the disease. That's true positive. Is that okay? So they have their different strengths and weaknesses. I'll put it down in that handout. I will allow you to read it. But what I just want you to know is that they are judges. They are measures, metrics to judge the performance of various models. So at the end of the day, you have to now do a thorough analysis and pick the best model based on popular votes among all these metrics. Is that clear?
Yes, sir.
John, that's clear?
Yes, sir.
Yeah, we'll give you more materials to understand better.
So thank you, Prof. We also have a question from Samuel. Samuel, go ahead and ask your question.
Yeah, good afternoon. Thank you so much, Prof, for this wonderful lecture. So I just want to understand a part of the code. Just like, for instance, now, this the one that is being shown right now on the screen. You can just leave it, Prof. I think since they are somehow similar. Yeah, so they are somehow similar, yes, sir. So like, for instance, now where we have both SVM model, train overweight tilde dot. So what I want to understand is that it's like when you were explaining, you said, for example, now using this overweight as an instance, that it is a function of some maybe other variables. But I'm seeing here that those variables are not clearly stated here. So could it mean now that this data used in this particular place only contain all those variables together with this response variable overweight? Or there are others? Because I'm just trying to think of what if I don't want to use all those variables, maybe just specific variables. So how do we handle that? So
that's a very great question. That's a very great question. I can just demonstrate that to you right now. Let me see the code that we have. Let me just demonstrate from one of the models. Let me go to let me go to one of them. I said it, I mentioned it, or maybe you didn't. Okay, look at this one now. Maybe this, let me look for one that will easily run. Okay, maybe this LVQ. Now, this is the response variable, right? This is the response variable, output variable that we are trying to predict. Now, if you want some specific variables, you can just say them, put them there, and use plus. I said it. Use plus to get them. I mean, to put them there. Now, these are the names of the variable. Let's say, which one do you pick now? Let's say you want to put age, rigor, and sex and fever there. Okay, let's have it. You just say age, the same way it was spelled, please. Can you see? John, can you see? Age plus, you see? Is that answering your question?
Yes, sir. Yes, sir. Yes,
plus,
sir.
I said it, maybe you hadn't come. Because if you put dot, I said, even if there are 1,000 variables there, to pick all of them. But if you wanted some specific variables, you just put it, you just label them. Let's stop here for now. You can see, if I miss the spelling, it won't run. So look at that. Can you see it ran? Can you see?
Yes, sir. Yes, sir.
It ran. So you can just specify like that. If you wanted to even put square root here, raised to power something, you can still do that. You get it.
Yes, sir. Yes.
You can do
Thanks so
anything.
much, sir.
Yeah, you can say square root of age, it is still wrong. Maybe of age, it will run. Let's put sex in. Or even that sex can still appear since they are now different. Is the square root of age is different from age itself, isn't it? So it will still run. Yeah, you see. Can you see it's running? It has run. So you can do a whole lot of things here. So it's very, very fantastic. Any other question? And you can use Control Z, like your word. You can just use Control Z to return it back. Can you see what I'm doing?
Thank you,
Question?
Prof.
Yes, please.
We also have another question from Depla. Kindly ask Professor your question. Depla?
Hello, Prof, can I ask a question?
Thank you, Prof, for
Okay.
the lecture. Please, my question is regarding the interpretation of specificity. There was
Yes,
a point that the specificity was 85%, but you said it was low. So what's the cutoff for determining high and low specificity and also for sensitivity?
Yeah.
Thank you.
Thank you so much. I didn't say it was low. Specificity is low. Is high in that regard. If it is 85%, it is high. Once anything is above 50%, is relatively high, isn't it? On a scale of 1 to 100, isn't it? Isn't it?
Yes.
But what specificity is concentrating on is that it is concentrating on the true negatives, while sensitivity is concentrating on the true positives. And in actual fact, sensitivity is more popular than specificity because we are usually more interested in the number of people that are positive to the disease, isn't it?
Yes.
Isn't it?
Yes.
Isn't it? Yes. So if you now have a model that is now giving you high value for the number of people that are not having the disease, it doesn't really help you what you may now want is to really tweak the model a bit and track the model a bit so that it will give you the true values of the people that are positive to the disease so that you don't misdiagnose. You know, when you're supposed to be treating typhoid, you are treating malaria so that you don't misdiagnose. And the misdiagnosis, this topic is very important, even to malaria modeling and infectious disease model, because machine learning can be used also for diagnostic purposes. And misdiagnosis is a very great problem in health science, in medical science, because it can even lead to legal actions and a lot of other things. That's why, because of the accuracy, high accuracy of machine learning models, we have embraced machine learning methods for also diagnosing these diseases. And that is why if you write any paper and you are able to do thorough job and you put all these things there to diagnose or to predict the nature of any disease, be it malaria or any other disease. You can see there's another experiment I'm conducting here on overweight, which is also a very global problem on overweight. Maybe I'm going to do that in another class. If you are able to predict these diseases very well, then your paper is likely to be accepted and be well cited, right? So that is something we can ponder upon.
Thank you.
Thank you, Prof.
I have also a question.
Yes, please. Maybe
First
we
of
may
all,
not. Okay. Go
First of all,
ahead.
I'd like to thank you for having this wonderful webinar. We've learned a lot. My first question goes to data partitioning, where you mentioned that we can partition our data into the training set, the testing set, and the validation set. Now, I wanted to ask, under what condition do we use the training and the validation set? And under what condition do we use training and the testing set? Or can somebody just partition the data into the three sets and use all of them together? Or there are conditions one has to consider? I don't know. Another question is on suppose before I model the machine learning model we've learned, let's say, for example, in this case, let's say I estimated the binary logistic model, and I realized that some variables were not significant and some were significant. Now, before I move to now a machine learning model like KNN, do I have to remove the other variable which were not significant, or I can just proceed and estimate my machine learning model with all the variable, whether significant or insignificant? Thank you.
These are great questions. These are great questions. Now, under what condition do we use the validation set? You see, machine learning is very rigorous. Although it may appear simple, it's very rigorous, especially when you are in the practice, when you are in the industry, you are really, really practice, or even in academic, because you want to write believable papers. Now, there are sometimes we go ahead and do the partition the data into three sets. We'll call the first one training set, the other one test set, the other one validation set. It may be in the ratio 60, 20, 20, right? So that you still want to test again, you still want to be sure again. It's just bordering on being sure again, just being sure, doing it over and over again, just to be able to get the best results. But sometimes, even if you divide into 3 or you divide into 2, it may still give you the same results. But for some data sets, if you divide into 3, it can give you different, maybe higher accuracy or something, or sensitivity or thereabout. But majorly, just do as much as you can to be able to get the best results, right? Because by training each model on the training set and also even evaluating them on the validation set, you can select the best performing model, for deployment. So that answers the question for that. Then the second question is that if I like this feature importance that we are doing, that which one are we going to say? Well, should I go ahead and is this what you are saying? This one. Let me use this one. That's the one for square root. This one. Is that what you're saying, that we should just, you mentioned significant. There's no significant here. Be careful of significant. Is that okay? This is not p-value. This is not statistical modeling. If you measure anything significant, that language, we don't like it in machine learning. They can reject your paper. It has happened to me before, sometimes ago. So significant is not the case here, but we're just looking at the order of importance, as you can see here, order of importance. So it is left to you. It depends on the policies of your company. If you want to pick the best out of these ones, maybe you can take any threshold. You can stop here, or you can, there's no particular threshold here. You can decide to stop here, or you can decide to pick the best 5 or the best 3 and use for your final model deployment. It depends on the policies of your organization or the research questions at hand. Does that answer your question?
Yes, it does. Thank you.
Thank you, Prof. We also have 2 people who have questions. Let's start with Segu. And I'll request Prof, we give them the opportunity that they ask the 2 questions, the 2 of them to ask questions, then we respond to all the questions together because of time. Let's start with Segu, and then we have Erasupo. Let's start with Segu, please. Ask Professor your question.
All right, thank you very much, Prof, for your time and then for everything you've taught us. I just wanted to ask about a situation when you have the origin of the cases in the data set. And for example, say 20 locations, 20 origins, and that is also, contributing to whether, the severity, maybe of malaria severity and all that. How do we, rearrange our data set and then, prepare it for use for this? And that's one. Then number 2, I was looking at after everything, is there a possibility that we could do a ranking according to order of importance and say, okay, 50% for maybe sensitivity, and then maybe 20% for another condition, and then use that to select the results that we would use, maybe depending on the objective of the study. Thank you.
Yes. You've answered the second one, depending on the objective of your study. See, you are free to do any experiment you like. It depends on your audience. You get it. So machine learning, that's why the name. You can learn, you can divide your data in any way that aligns with your objective. And even the first question, you can pick, rank your data in any way that will align with your objective. There's no hard and fast rule about it. That's why we have the no free lunch theorem. Just do something that your objective matters in machine learning. But one important task to work with, or to always imbibe, is to try as much as possible. Try several methods, several techniques. Don't just do one and stop, right? try, that's why in most machine learning papers, if you just present only 1 or 2 tables, that paper is not likely to be accepted. You know, if there were time, this is just one result. I could give 4 other results. In fact, the whole place will be filled with results. So please do what you think is good in line with your specific objectives. And in most cases, machine learning tasks are used mostly in industries, and they must have given you what they want to achieve. So you are likely not to have that kind of problem, because you are going to be helped to work alongside with the objectives of the organization. Is that okay?
It's fine, sir. Thank you, sir.
Okay, let's have the other questions quickly. We may not have practical sessions today. I'll just share the link. Is that okay?
It's okay, Prof. Please, I have another question, Prof. Can I ask? I don't know.
Maybe in the next series, we'll just allow all of you to practice that day. Is that okay? I'll just
Yes,
teach.
sir.
I'll just
Yes,
teach
Prof.
30 minutes, and then I'll be watching you practice and share you into groups. Maybe that can be fine.
Yes. Okay, Prof. I have another question. I don't know if
Please go ahead. Please.
Kindly let us be through moderator. We have Isaac first. Isaac, ask your question.
Okay. Thank you so much.
Okay, are you calling? Oh, sorry, I thought I was being called.
So
Isaac?
my question is similar to the previous speaker.
Yeah, I'm here, but somebody's already asking question. So maybe he should be done with his question. So I'll ask my own after his own.
Okay, Prof. Okay. So as I was saying, I want to know, is there any type of data specification that can best work in machine learning model? If so, I want to know one of them, because you mentioned earlier that when you have a categorical data and numerical data, you can use machine learning. So I want to get it clear which type of data best work with machine learning. Thank you. Then the second question is on the kappa values. When you are running the model, some kappa values are reading negative, some positive, some even 0. So I want you to shed more light on this. What is the interpretation when you have negative kappa value and when you have positive? Thank you so much, Prof.
Yes,
Thank you so much, Dr. Adamu. So he said, what's the data specification? You see, data scientists spend 70% of their time on data preprocessing data. Because if you put in garbage, you will get garbage in, garbage out. So as you can see, by the time the data I used was already prepared, I told you it had even been probably published somewhere. So you could see it was faster. Otherwise, we could spend even 6 hours trying to dress that data set. And that is why machine learning is a very big aspect of data science, because it is highly data-driven. You must pay good attention to your data. So the kind of data we are using is usually a CSV data that, for instance, for supervised machine learning, is the one that will have output and what? Input. If your output is categorical, what do I mean by categorical? Maybe has the disease or does not have the disease, does not have the disease, yes or no, profit or loss, something like that. That's categorical output. That is what you want to predict. Then you are looking at classification problem in supervised machine learning. Or if your output is continuous, like age, weight, weight of the patient, like height of the patient, you want to predict the height or something, or the blood pressure even, then that is a regression problem. So pay much attention to your output variable. Let it be well set. It could, and you have to code it 0, 1, or if there are more than 2 cases, that's multi-class case, then it could be 0, 1, 2, or even 1, 2, 3, right? Code it, put it well in an Excel sheet, code it well. And as you can see, the data I used here was well coded such that it is easily acceptable and interpretable by the algorithms and easy to run. So code it well. Now the features, it does not matter if it's a mixture of categorical and numeric. It does not matter. But pay much attention to your output. Is that okay? And set your data well and let it be well put in your Excel sheet. Now, let me run this data for you. Look at it. Look at it, well coded. Look at it. Not severe. This one, the algorithm can still take it. You could see I wrote a particular code up there to interpret this one for it, to interpret this one. Otherwise, if you have all your data set like this in an Excel sheet, probably preferably in CSV format, you can see 0, 1, 0, 1. Whether he has anemia, if he does not have anemia, it's 0. If he has anemia, it's 1. You just code it like that. Jaundice, if he has jaundice, it's 1. Doesn't have jaundice, 0. Just like that, you can see. And look at age, just put it there. You can see. Even maybe they can take weight, height, or something. You can put everything there and just set it up like this. If you look at the Excel sheet of this data, I'll send it to you. It's very beautiful, looking very neat. Then that's the type of data that machine learning algorithm can take. And if we are going to publish any paper, this is the type of data I want you to prepare so that we can mentor some of our young colleagues on how to publish machine learning paper, especially for malaria modeling. Now, answering your second question, the Kappa statistics is a very powerful statistics that helps us to judge the agreement between the model prediction. You know, the model prediction is divided into 2. The actual that we have and the one that the model is predicting, actual predicted, actual versus predicted. So Kappa is really the judge for that one. And it ranges from -1 to 1. It means from -1 to 0 to 1. Are you getting me now? If it is 1, then it means perfect agreement between the model predictions and the actual labels. If it is 0, it is just equivalent to chance. It is still not too bad, but it is equivalent to chance. If it is less than 0, then it is worse. I hope that answers your question.
Yeah, thank you, Spogo.
Great. We have about 10 minutes. What do we do with the 10 minutes?
Yeah, Prof, I'm supposed to ask the last question, sir.
Oh, okay, my friend from, oh yeah, please go ahead.
Yeah, good afternoon. I would thank you so much, sir, for that lecture. It was actually very beautiful. So my question is that, yeah, in the Caret package that we use. Like we said, we had close to or more than 200 200 models there. So and
Yes, please.
here we selected 10, we used 10. So one, I want to know, is there any, what are the criteria for choosing the kind of model that we selected, and how many be good to go? Because you said we cannot just pick one and then say that's all right. That we have to pick as many as possible so that we can compare models. So how many be good for us to go, and what will be the criteria for the one that we select? Sir.
Oh, now that's a very good question. You said how many will be good to go. It depends on your time. You can do 50. Depends on your time. It's just like what you are asking is like, how much data should we collect? Depends on your time and resources and what your laptop can carry. Some of those models are highly advanced that will require you to load some packages, some preloading of some packages before they can run. Is that okay? Okay. So it depends on your time and your resources, or the resources of your company or your organization. So that's why there is what is called parallel computing. If you have, sometimes your Windows may not be able to carry some of those models. You may even want to use a MacBook or high-level laptops that has higher cost. So, but it depends. But anything from between 5 and 10, 5 may be too small, maybe 7, 10, you should be good to go. It's like asking questions from, even if in your organization, if you have to form a committee, how many are usually in the committee? By the time you have committee of 50 people to judge, to talk on a matter before it can be ratified as a policy, it may be too much. It depends on the largeness of the department and the resources available. Maybe they even have to pay each committee member. So if you have sometimes 5 committee of 5 people, 5 good, knowledgeable people, they can do justice to the matter, isn't it? Sometimes committee of 10 people maximum can be okay. By the time it's getting to 15, well, it's fine. But what I would advise, you can do between 7 and 10, then you compare with before hyperparameter tuning, then you do it again after hyperparameter tuning, then you do it again, maybe before balancing and after balancing and all that. Is that clear, Akin?
Thank you, sir. Yes, sir. But I also ask that what determines the model that is selected among those that we use, sir?
Yeah, that's what I'm saying. Those are popular models. Those are just the most popular models. It's just like in a house or in any organization, there are some people, you want to form important committees. There are some people you cannot leave out, isn't it?
Yes, sir.
From past experience of what they've done before. Is that okay?
Yeah, that's true, sir.
You do agree with my answer now?
Very well, sir.
Yeah, that's just the answer to that.
Yeah, thank you so much, sir.
You are welcome. 1 or 2 more questions before our moderator wraps up. So in this particular...
Sorry, Prof.
Yes.
We have about 3 minutes. And we have 1 question from Lopat. Lopat, kindly.
Final question, okay.
Yes, thank you so much. Can you hear me?
Yes, loud and clear.
Yeah, thank you so much. I'm Robert Megija, a PhD student in Moi University, second year, beginner of research. I really have the interest of machine learning and AI, which I found this to be very insightful. So though I have joined very late, but how I wish that the materials are shared, but I chose to not to ask a question, but to give some references to
Robert, we can't hear you.
those measures that Prof has discussed, so that if any
Sorry, Robert, we
needs
can't hear
to
you.
understand, to get more understanding about it. Yes, I'm saying.
Yes.
Maybe you can type your question. Maybe you can type it also.
Yeah.
Robert, kindly type your question.
Hear me again?
We can't hear you.
Hello.
Maybe you can type your question.
Can you hear me?
You can type it.
I think
Prof, you
because of
can
time-
wrap up. You can wrap up now, Prof.
Okay, so thank you so much, Prof, for that nice presentation, and we are happy for the people who have attended our first monthly webinar series. We intend to have this activity.
Yeah, can you hear me? All right.
We intend to have this activity every month, the last Saturday of the month, and we intended to have hands-on session today, but it was not possible. Maybe I will discuss with the professor so that our next session, we can make it more practical.
Yes, yes.
Yeah.
Actually.
The next one we can make it more practical so that people can learn how to do the coding and learn machine learning models. We are also informing members that we have formed this group, machine learning network group. If you'd like to join, kindly let me have your number and I'll make sure I've added you in the group. And in that group, that's where we'll be sharing a lot of information relating to the materials and the many activities that we'll be doing through this group. Professor is our leader, and I know there is a lot that you guys are going to learn pertaining artificial intelligence and especially machine learning. Prof, you can add something? We have just few seconds remaining.
Thank you very
Go ahead, Prof.
Thank you very much, Prof. Dennis. Thank you all for attending today. Please support AMMNet and support our machine learning group. We are interested in capacity building and helping you further your career. I want to wish you the best, and we hope that you can contact us for more mentorship. Have a wonderful time and enjoy your weekend, everyone. Thank you all. Bye, everyone.
Thank you so much, Prof. Kindly, I can give my number where they can send their details so that I can add them on the group.
Thank you,
This is
Prof.
my number. Kindly, let me send you. Let me type my number.
Yeah, thank you, Prof. Thank you so much.
Yeah, that's my number. Those who would like to join the group, you can send me your details through that number.